785 b plus I sine of 0.785. Similarly for the one that has minus here, and then you do a lot of algebra, and if you do the algebra right, all the I terms will cancel out, and you will be left with the real. If you are not left with the real, it means only one thing. You messed up the algebra. So you could have done it this way, okay? But it would honestly take at least 2 hours of very careful and strenuous algebra. Yes.
You forgot a zero, the point 0 minus 7. On the E, the last E.
Oh, a 0. Yeah. Thank you. It's a 0 here. Okay. Okay. So that's path 1. That's exactly what we've been doing until now. With me? Any questions about this? All right. That's not what we're going to use. It's luckily a much better approach in terms of algebra. And we can also do it on the computer. By the way, we couldn't have done this on the computer because Excel doesn't have complex numbers. So, so now let's continue up here, and I'll erase this to continue with the in-class exercise. But please have it in your notes. I hope you completely understood that. Everything okay? Okay. So if you successfully did the homework, last problem with this method, congratulations. If by any, well, John, if by any chance turns out that it was right, give 3 point bonus. Alright. So we found the denominator roots. We have a complex conjugate pair. Actually, let me write. Still not going back there, just general theory. When we have a complex conjugate say A plus or minus IB. You can rewrite S minus A minus IB times S minus A plus IB, which is the factorization of the complex conjugate pair that I just erased, okay? S minus A squared plus B squared. Okay? Just do algebra. You get S minus A squared minus I squared B, but minus I squared is minus 1, is plus 1. Minus I squared is plus 1, since I squared is minus 1. And then the cross terms cancel out. You have S minus A times minus IB plus S minus A times plus A. So this product is always going to be S minus A squared plus B squared. Okay? And you can do an alternative expansion. Remember, we would have partial fractions expansion gives us, see, let's say, I'll just put A, okay, let's say C plus S minus A minus IB. Here, C1. I'll just put C1. A plus would be more confusing. Plus C2 over S minus A plus A. Right? That's the normal partial fraction expansion if I have this product. Clear, everyone?
Yeah.
Bring them at the common denominator. And then if you bring at the common denominator, we have the product of the two. And the product of the two, as I showed you, is going to be S minus A squared plus B squared. And you have here C1 times S minus A plus IB plus C2 times S minus A minus A. With me? And you can redefine the C's. What do we have in the denominator, in the numerator? We have 2 degrees of freedom, C1 and C2. And we have terms that are linear in S, C1 plus C2. And we have terms that are constant, C1 minus A plus IB plus C2 minus A minus IB. So you can rewrite that in the way you normally see it in books. In books, you normally see it as, let's say, C3S plus C4 over S minus A squared plus B squared. With me? So that's what you normally see in books. Now, you can work with that to get directly an inverse without having to go through complex at all. I make a little twist of this that makes it more convenient and more efficient. If we look at an expanded dictionary, and I'm going to have 2 additions, I gave it to you a little bit before, additions to dictionary. F of t, F bar of t. E to the minus at times sine omega t has Laplace transform omega over s plus a squared plus omega squared. And e to the minus at cosine omega t has Laplace transform s plus a over s plus a squared plus omega squared. So if I have things like that, I can immediately invert like that. This would immediately invert like that. This expansion, you would have something s plus something constant, and you would have to do some manipulation to bring it in that form. Instead, you can redefine constants and do an equivalent expansion to rewrite now this now capital A, S minus A, plus capital B times little b over S minus A squared plus B squared. That's the alternative expansion that I am advocating. And how do you find the parameters A and B? Easiest way, use the alternative expansion and just use 2 values of S. And solve it just for 2 values of S next time. Okay, so what I'm saying is, our first method, we use this partial fractions expansion. And I discussed how we would proceed if we had used this partial fractions expansion. With enough determination and carefulness, we can carry it through. However, there's a much easier way of doing it. And the much easier way of doing it is, instead of doing this expansion, replace these 2 terms by this combination. And then this combination inverts immediately. What's the inverse of this? The inverse of this would have been a e to the plus at, since my minus a is plus a there, cosine dt plus capital B e to the AD sine B. So let's do that in the in-class exercise 2. All right? Got a question? What did you do? You doing good then? Okay, got it. Did I go too fast? More time? If I go too fast, I need more time, tell me. Brian and Andrea, okay? Okay? All right. So, going back to the in-class exercise. So we found we have a complex conjugate pair. So instead of using the standard partial fractions expansion, we're going to use the alternative expansion, which replaces every complex conjugate pair by a term like that. Okay? So, alternative, since we have complex, now this you turn it, okay? Complex conjugate pair, we will use an alternative partial fractions. And that's going to be that s plus 1 over s fourth plus 3s cubed plus 2s. I will not write all the digits here, but I will use all the digits in Excel. In Excel, it's important to use all the digits. Okay? Equals. So, instead of writing for this complex conjugate, I can write A. The real part is 0.0979, S minus the real part. Plus capital B times the imaginary part, which is 0.7850, divided by S minus 0.0979 squared plus 0.7850 plus C31 over S plus C41 over S plus 3.195. We use all the digits when we do it. So I want to make sure that this is completely understood before we move. As we did previously, the regular expansion would have had C11 over S minus 0.979 minus 0.0795I plus C21 over S minus 0.0979 plus 0.07585I. We did that before. Instead of this pair of terms, I'm combining them S minus the real part squared. The real part of the complex conjugate pair is 0.979 plus the imaginary part squared. Okay, this is S minus real part squared, and this is the imaginary part. And in the numerator, I have A, S minus real part, plus B times imaginary, which is in the dictionary. What do we have here? One part has S plus A squared, S plus A, omega squared. So notice, this is the this is the sine. I can get C31, C41 with quick and easy, and A and B with two values of S, any two values of S. By the way, several of you in the exam, you had three C's to determine. Several of you used only one equation. For three unknowns, you need three equations. One equation, you have infinite solutions, and the chance that you got the correct solution is practically zero. One of you interesting lab used two equations for three unknowns.
Are you talking about on the computer part of it?
Yes.
Well, on the computer you have these three equations, but you want to just write out all three of them?
No, in the Excel.
Okay.
Used only a single function. No constraint. Function is just one value of S for the three C's.
On what we wrote down on the computer part, it was fine.
It wasn't what you wrote down. If you did write on the computer, you're fine. Okay? All right. So, we're ready now to go to the computer. Felix not happy.
It was raining. You knew it was coming.
All right. So, hold on, I wrote it up there. Well, if I put it down, I think and go. Still living now.
Is B okay? What is B and A? Is that just
The capital A and B?
yeah?
Yeah,
No.
they're the parameters. They replace C11 and C21.
Okay. Okay, got it. That's what we're looking.
Okay?
Gotcha.
Originally, this part was C11
Yeah.
over S minus this with the plus C21 over S minus this with the minus.
Got it.
The C11 over S minus plus C21 over the S minus can be rewritten in this form. You could do a lot of work, find C11 and then calculate A and B. This is stupid. It's much easier to find A and B directly. Yes?
Is that an alternative partial fraction expansion?
Yeah.
Or it's a
Yes.
partial fraction
Alternative
expansion
partial
of the
fraction
first one?
expansion.
But is that a partial fraction expansion of the first one?
Mm-hmm.
The A and B is
Yeah, that's an alternative partial fractions expansion for this. What I have here.
so it doesn't have to do anything with the first one, the C11 and the C21?
No, it's the same.
It's an alternative to that. You could do it either C11 over S minus this guy with the plus C21 over S minus this guy with the minus, or this term.
Yeah.
Okay.
He did that because they're imaginary terms, so that way it's easier.
Okay? You can rewrite the original C11 and C21 into this guy that has a capital A and capital B. And it's a lot easier to find the capital A and the capital B than to find the C11 and the C21. And furthermore, this inverts directly, while it is very painful to try to get what you get from C11 and C21 and translate it to real using the Cauchy formula, the e to the I theta formula, etc. So it makes a lot more sense to do this partial fractions expansion whenever you have complex quantity pairs instead of the original. Nothing wrong with the original. Theoretically correct, okay? We could have done it that way. But instead of finishing this in half an hour, we'll finish it now, we will be taking the full second period and you all being glassy-eyed, and me being glassy-eyed. Okay? I've done it a few times, originally. Hello. Hopefully I'm improving my lectures, by the way. All right. So let me go with the screen. What is this?